Cast is now starting on only mode.
Good morning, ladies and gentlemen, and welcome to the SAIEE Nuclear Chapter webinar on small modular reactors, a review of status of the gas-cooled reactor projects. Before we start, a few webinar considerations. Attendees are reminded to ensure the volume is turned up on your device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. By default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other, however, are encouraged to ask questions. A recording of this webinar will be made available on the SAIEE YouTube channel, SAIEE TV, under the Nuclear Chapter playlist. You will find the registration link to the SAIEE TV in the chat box. Please register. It is free, and then you will receive notifications when we do another upload of another upcoming webinar. A certificate of attendance will be issued a few days after this webinar. Just something about the small modular reactors, as you know, have increasing potential for power generation in the future. And this presentation of Prof. David Nichols is the second of 4 webinars to discuss the key issues, positive and negative, with gas-cooled reactor technology in the SMR field. It will also cover the status of the major SMR projects using GCR technology. And of course, our next webinar, which will be on the 22nd of May, will be discussing cover molten salt and liquid metal cooled SMRs. So please be on the lookout for the registration link. I'd like to now introduce you to our speaker today, David Nichols, who is also the chairman of the SAIEE Nuclear Chapter and was appointed as the chairperson of the board of the South African Nuclear Energy Corporation, NECSA, in January 2020. Prior to his retirement at the end of December 2018, he was the chief nuclear officer at Eskom. Internationally, Mr. Nichols was the chairman of the IAEA working group for reactors from 2010 to 2016 and is currently the co-chair of the IAEA Technical Working Group on Nuclear Power Plant Operations. He was a member of WANO's post-Fukushima design review team from 2012 to 2018. So you know we are here in the midst of a nuclear expert. Over to you, David.
Thank you very much, Minx. I'm always embarrassed by some of these statements. Now, why is my mouse not letting me show the screen? Something's going. Why is my system not working? I cannot get my screen to show. Sorry, I'm just having a problem here with my system. It is not letting me in to show my screen. For some reason.
I'll make you presenter, see if it happens.
Okay, that looks good.
Okay.
There. That's better. Okay, thank you much indeed, Minx. Okay, welcome all. I'm going to present gas-cooled reactors. Clearly, it's one that I've had a lot of background to. For those who know me, we ran the PPMR project at Eskom, which we can argue was the first SMR ever built, ever that proved the concept that small modular reactors could be commercially viable or had the potential to be commercially viable. So I'm going to go through this presentation. The first couple of slides are the same slides I did last time, so don't worry if you were here last time. So what is a small reactor, which is a common thing, and then I want to go design options of high-temperature gas-cooled reactors, and then the advantages, limitations, and then current designs and status of those designs. So I'll try and go through reasoning. So what is a small modular reactor is the first question, and the answer is it's a reactor as initially defined as between 30 and 300 megawatts electrical. Now, why it's interesting is because I remember back in '95 when we first put the PPMR on the table at 100 megawatts, we were told in Vienna, I've been told quite strongly in Vienna, that clearly we were not a commercial discussion because they had decided that small reactors were 600 to 900, medium and 900 to 1200, and large were 1200 plus. So 100 megawatt wasn't commercial. That view has changed in the world. What's the logical thing is that smaller makes you build more of them, makes you learning and you learn faster. So standardized machines. So technology with inherent safety, a lot of technologies developed over the last 50 years, 60 years, which were not put into the marketplace, but were proved quite competently by large test reactors and safety being such a dominant issue that if you can get inherent safety in the reactor, you get increasing public acceptance, and therefore limit. So the key thing for small modular reactor is small unit size, which limits the financial and risk and exposure. In other words, when you buy them, I'm going to commit to 1,000 megawatts and $5 billion. All the SMRs in the world today are talking about technologies which have actually been developed, not put commercial service necessarily, but been developed. And they're all looking at operating both cycle and load following flexibility. And the key thing in an SMR program is absolute standardization. Okay. And you can see this with the classical approach. Values of death of any major project, and all projects you look at, just be aware that there is the view where you start off at the beginning, where someone does some fundamental research, quite cheap, quite interesting, what's called technology readiness level 1 to 4, and you need support to get to the point of being able to say, this thing actually works and is viable. Then you've got to move it into a commercial discussion of building a prototype, pilot production, and so on. And that again is a major pile of money, and who pays for that is always a question. And the last one, which is the simplest one, is when you've got this thing deployed, and can you sell enough to make commercial viability? Just worth bearing in mind that those are key elements, and they're ones that every single SMR in the world is facing these problems. So let me go on and talk about what, and this is probably the most important slide in a sense of all of them, may seem odd to people, a simple slide. What are the options? I'm going to go and build a high temperature gas-cooled reactor. What options have I got? Well, the first option you've got is between Prismatic and Pebble fuel. Pebble fuel is those, which you'll see, I'm sure, those 6 centimeter diameter graphite balls which are impregnated with coated particles, and these are handled, and you've got on-load fuel handling, so you can take fuel out the bottom of the reactor and put fuel in the top while it is running. And this very much was the German development. Professor Schulze at Munich in the 1970s and through into the 80s. It has advantages. Its biggest advantage is simple, and that is that you could do on-load fueling, so you never shut the machine down for refueling. The alternative was called prismatic fuel, also called block fuel. This is fuel where you have blocks of graphite machined, normally prismatic 6-sided blocks of graphite, which are embedded with uranium dioxide, tracer particle fuel. And the decision when you get prismatic fuel is, are you going for a fuel cycle, i.e. you shut down every 18, 24 months and you refuel, or are you going for lifetime fuel? And what you'll see later on is that, in my view, if you're going to build a prismatic core, your problems are that your fuel efficiency is way lower than Pebble fuel. Pebble fuel gives you much better burn-up efficiency, enrichment to burn up. And the actual problems of fuel cycle operation becomes an issue. And if you know a bit about how unloading cores go, Kuberg has 157 fuel assemblies. You pull 157 fuel assemblies out, put them in the spec fuel pool, then put them back in at the end of the outage. With a block fuel reactor, the classical GTMHR, which was one of the block fuel reactor in the 90s and 2000s, was in fact 10 blocks stacked in each of those 157 positions and 10 deep. So there's 1,570 to take out and then reinstall in a particular order. So the refueling time for a block fuel reactor is, by all intents and purposes, seems much longer than that of a light water reactor. But the advantage is you can go what I'd call lifetime fuel, which is being pushed for several designs, where essentially you build a core in block fuel. You don't ever try and refuel that core. You put the core in, you run the core till the end of life, then you take that core, put a new core in. And that could be in the factory or in the shop. So you'll tend to find that grid scale SMRs, let's say 100 megawatts thermal and upwards, tend to be pebble bed fuel designs. Small reactors, which are aiming to be based on almost replacing diesel generators, 1 megawatt, say to 5 megawatts electrical, tend to be block prismatic fuel, with the idea that the whole thing gets taken to and from the site. Okay, having put that concept, the next thing you've got to decide is, do you go for a direct or indirect cycle? And I'll mention a bit more of this. If you go for direct cycle, you've got a gas turbine into your helium circuit. This is what the PBMR did. Almost nobody else is doing this at the moment. It was stopped as an idea, primarily because it was seen to be too much of a leap to begin with. I would argue that heavily. But if you go for direct cycle, the advantage is that your high temperature components, seeing the high temperature steam, high pressure gas or high temperature gas, is not the pressure boundary. Because the pressure boundary, by definition, if you're an indirect cycle, that is that you have a primary circuit of helium and a secondary circuit of something else, then you clearly got the pressure across that pressure boundary is the full system pressure. And whatever temperature you're using as your hot gas temperature is the temperature that it must be able to survive. And clearly, if you get above that 750 degrees centigrade, that becomes really difficult. So you'll find that indirect cycles tend to have lower temperature operating temperatures than direct cycles. And once you've decided to go for the indirect cycle, the next choice you can make is, do you want to go for a steam cycle on the secondary side or a molten salt? In other words, do you want to use a molten salt system where you pump molten salt into your heat exchanger, heat that up to the temperature, and then have that feeding downstream? Has significant advantage being molten salt. The biggest advantage is storage. You, in theory, can have your nuclear reactor running at, shall we say, 100 megawatts equivalent full power, and have a steam turbine that's 200 megawatts power, and then you load follow the turbine, but the reactor stays at full load the whole time. Interesting concept, hasn't been built, but it's been demonstrated in the CSP, the concentrated solar plant, where you've got you may have seen them, where you've got mirrors reflecting onto a heat tower, and that heat tower heats up the molten salt, and the molten salt then drives the turbine. This is used for solar plants as a way of getting dispatchable power out of a solar input. Only trouble is it comes in very expensive and hasn't been pursued very far. Being pursued to a point of proving its costs. The next key question of design, which again is something which is not really being looked at by many people, but it is we did that in South Africa when we did the advanced high temperature reactor in 2016, 2017. In ESCOM, we looked at it and we decided it was a better solution to go for a concrete pressure vessel. And now you might say you don't build concrete pressure vessels, but the British advanced gas reactors are all concrete pressure vessels. And they are markedly cheaper than steel pressure vessels for nuclear grade steel. The advantage of concrete pressure vessels is a cost, but also the fact that the problem with a high temperature gas cooled reactor, the only safety issue which we can really say is not been properly resolved, is that of a catastrophic disassembly of the core. In other words, the core is critical as it's designed. You then have a rupture of the pressure vessel, and the core nominally changes from being a cylinder of pebbles to a sphere of pebbles, and hence goes critical above a temperature. Difficult to imagine that happen, but when you're down to discussing probabilities of 10 to the minus 8 per year and worse, then you would prove that it can't happen. And the nice thing about a concrete pressure vessel, it has no failure mode that fails in that manner. It cracks, it can leak gas, that is clearly true, but it hasn't got a rupture like steel. So that's probably an interesting design. Again, hasn't been done. It was done on the advanced high temperature reactor in South Africa in 2016, 2017, in conjunction with some UK engineering teams who had worked on the advanced gas reactors in UK, which are clearly getting old now. Absolutely no good. And then clearly always the question is the degree of factory construction. The degree to it, and you'll see some really small reactors on the list I'm going to show you in a second, which are designed to be transportable. In other words, you actually physically build your reactor in the factory, put it on the back of a lorry, take it to the site, plug it in, use it for its operating life, 10 years, 15 years, 20 years, and then take it back from the factory and refurbish it and change the fuel. Hence, I come back to the lifetime of fuel, which is a very interesting concept and I believe has a great deal of credibility. Interesting. Okay, one of the advantages of gas-cooled reactors, why I'm talking about these things. Okay, if you at my water-cooled one last time, I said that the water-cooled technology base was fully proven. Gas-cooled reactor is reasonably proven technology base. We've run reactors across the world, in the UK, in the USA, in Germany particularly, and now running one in China. So the answer of saying it's never been done before, no, it's been done. It's been done for a commercial period. The AVR in Germany ran for 22 years and wasn't shut down because it was seen as the end of life. It was just that it finishes its job. And so the technology base is reasonably proven. We know the answers and the questions involved. As long as you get the gas temperature below about 70 degrees centigrade, there's no exotic materials required. I mentioned earlier that if you're going to build a pressure vessel, if you're going to build an intermediate loop, then you need to have a heat exchanger with helium on one side at your gas temperature and your coolant on the side, molten salt, steam, whatever it is. And up to about 750, that's pretty much doable. There's no great debate. We can do that. That's very similar to a coal-fired station in many ways in terms of the upper end of the temperatures. It can be done. Clearly, if you get beyond that, you get exotic, and that's where you end up with looking at, well, where you've got higher temperatures, you can talk about going for a direct cycle because your temperature drop occurs across the gas turbine, not across the pressure boundary. And the gas turbine hasn't got a safety issue. What's also interesting in what we did in the Advanced High Temperature Reactor in 2016 was we planned to do a combination of these. In other words, we planned to have a small high temperature gas turbine, a ceramic gas turbine, dropping the temperature from 1200 to about 700 degrees centigrade. And then it would then go to a heat exchanger. So with a hybrid system, it looked extremely good. There was no technical issues that worried us. I mean, everything worries you, but it wasn't really. But it's interesting. Very high temperature for process applications. If you want to go serious net zero and get rid of fossil fuels to drive high temperature process applications, creation of steel, then when you start talking about temperatures of 1,000 degrees centigrade, then only gas-cooled reactors can really play in that space. You've currently got the water-cooled reactors that are only about 300 degrees centigrade. You've got the lead-cooled and so on, which are looking at about, let's say, 600, 700. But the gas-cooled reactors have only got limitations. In theoretical limitation of a gas-cooled reactor with an idealized fuel would be about 2,000 degrees centigrade. So very good for that. The other point to bear in mind, which is one of the fundamental ones, it's got inherent safety without coolant. What that means is in every other reactor, you assume the coolant will stay there, at least some pressure, around the fuel to remove heat from the fuel. The Pebble bed, or the classical HTGR, assumes the gas all disappears completely. Depressurized loss of force coolant is called DLFOC, and it says you have a leak, you lose all your gas, and the plant will not overheat in the process. That is what makes it inherently walk away safe and so on. So all limitations, that sounds all very good. Why isn't the world knee deep with these things? It's got a medium pressure reactor vessel. In other words, it's running and it varies the design looking at, and they vary. The highest is about 90 bar. There's a number about 60 bar and so on. So your pressure vessel, it's not as high pressure as the water-cooled reactor, but it's still a credible, decent-sized pressure vessel. It's got low core power density. It is literally got one of the key things that drives all this is your core power density has to be down about 1/20th of a water-cooled reactor. Now that doesn't mean 1/20 of the vessel size, it means 20 of the core size. So the core is a much larger proportion of the vessel than in a water-cooled reactor, but it is a low core power density. And it's got limited power with inherent safety. What I mean by that is that there's a couple of issues around this one, but essentially, if you're building a pebble bed reactor and you cannot put control rods in the middle of the pebble bed, which you can't do in the classical pebble, the Germans did it with PHDR, a 300 megawatt, 750 thermal, 300 electrical in the early 80s, but it wasn't very successful driving a control rod through the middle of a pile of pebbles. But essentially, you've got a problem with shutdown. You've got to get core. So in a pebble bed reactor, you're really limited to about a 3.5 meter diameter core. Any bigger than that, and you can't get shut down. The middle of the core won't shut down if you shut the core down because your control rods are in the reflector. And even in a block fuel reactor, you're limited to about 600 because beyond that, your safety argument. You do overheat in the middle of the core if you have a lossable coolant. Okay, now I'm going to go through the number of designs out there. What I did was there's a whole pile of designs at various levels. I went to a document called the Small Modular Reactor Dashboard, second edition by the NEA, which is the Nuclear Energy Agency, which is a part of the OECD. And so I just pulled up the ones that they listed. I know there's a South African one, the Modular Reactor, which is not listed on their list. I don't know why. I also removed ones I did not think had any commercial future. So, for example, they mentioned the HTTR in Japan, which is a 30 megawatt test reactor. It's interesting, but it's not a production reactor. They also mentioned the Advanced High Temperature Reactor 100 from ESCOM. I know that it's not gone any further. So, and what they did was they put the dashboard into 6 key areas. And it's interesting, these areas are areas which they think, and it makes sense to me as well, are ones that actually drive you how ready you are to really become a commercial success. How well is your licensing going? Because nuclear licensing is fundamental. Have you got a site sorted out for the reactors? Have you got financing? Have you got a supply chain? In other words, have you got a manufacturing base to make your bits and pieces? Have you done an engagement? It's very interesting. If you look at you'll find interesting that you see the same with the water-cooled reactors and everything else, that if you look at the Russians and the Chinese, their engagement level is trivial. They aren't doing outreach to anybody else, they're doing it. Other reactors in the West are much more, got engagement sorted out, but nothing else has. And lastly is the fuel form that you're going to use, a proven and available fuel form. Those are the 6 things, 6 things that come out of this process. So I'll start, if I may. That's the list of reactors I looked at. I said earlier that there's a couple that aren't on here, and I can have an argument. So I just picked out the ones that was on their list, which I could get someday on. I start with, unless they're all in some kind of order, but in fact I start HTRPM, which is China, because it's commercial. It's the only one of these that actually is physically running commercially linked to a grid. And that's a 250 megawatt thermal, 2 reactors. Pardon me, I've got a bit of a flu today. The reactors, it's very much the German model design from 1982 being built today. It works, it makes power. I heard recently that they are now looking, the first unit is a twin unit, 2 reactors feeding 1 steam turbine. I've heard recently that they've committed, not true this is, but I heard from what I thought was a good source, that they had government approval to start construction of the next 2 sites, each of which will be 6 reactors feeding a single steam turbine. So they're moving forward on that one. BNAR is Wilcox Advanced Reactor. It's a 50 megawatt, and I put an assessment of where they stand design-wise. GTHDGR is in Japan. It's the only one that is a direct cycle in this list. I said I've taken off the ones that I thought were just going nowhere. It's 609 megawatt system design. The Poles are looking at a design, I'll come as HDGR Polar, and that's 30 megawatts. That one's interesting because it's aimed entirely at process heat. In Poland, they've got a lot of coal-fired process heat applications. They want to replace that with that. Leidos, USA, it's 1.9 megawatts. Again, you're looking at, this is thermal power, not electrical power. You're looking at things designed to replace to remote area applications. HMR 100 being the press recently in South Africa, 100 megawatts thermal, concept design. MOI is a micro modular reactor. And the same company is doing one called Pylon D1, which again is a transportable reactor. What you can see is a couple of these which you're looking at, and they've been funded in the US by the US government as part of military programs to try and get remote area bases. Evinci is a Westinghouse design, 15 megawatts. They're again transportable, and the XE100 is in detail design. It's the US Gascooled Reactor. It in fact is the South African. That should be 200 megawatts. I made a mistake here. Sorry, folks. That should be a 200 megawatt, not 100 megawatts. The XE100 is in fact the PPMR design, the final PBMR design, which will be looked at the end. The design team is largest African. Apparently, they hold design meetings in Afrikaans. Apparently, they're based in the States now. Okay, let's go through it. So what I'm looking at, I'm going to go through each one in turn. What you can see here is a classical. This is the diagram that comes out of this diagram. Bottom right-hand side is diagram coming out of the SMR, the NEA document. And what you can see is their view is here. It is indirect cycles, 2 units. It had a test reactor HDR10 built in China as a test bed that was started up in about 2001. Runs at 750 degrees centigrade, indirect steam cycle. And what you can see is very Chinese and also Russian. There were no Russian gas-cooled reactors at the moment, because everything is completed, done. Financing is clearly not fully there for follow-on machines. Supply chain is not fully there, but it's virtually there because they haven't got mass production. Engagement is they don't talk to people, they just do it. With a bit of admiration, I'll tell you that. So real project, if you're only going to buy an advanced a gas-cooled reactor today and place a contract for an existing machine, this is probably the only one you can actually walk in the door and say, give me a fixed price. The rest of it in alphabetical order. This is BNER, BDRX Technologies. It's 500 megawatt, 50 megawatt thermal, prismatic fuel handling, 800 degrees centigrade, a bit higher, but it's an indirect steam cycle again. Again, what you can see is in-house development project being funded in part by the US government, but really not good. In fact, most of them have that problem that they're not really fully engaged. GTR 300, 60 megawatt thermal with prismatic fuel handling. Developed with SAIEE, which is a Japanese Atomic Energy Authority. It's in conjunction with Toshiba and Mitsubishi, and so that's why they've got a supply chain all sorted out and financing, but not much else. And it's had a test reactor called the HTTR, which is 30 megawatts, and it's got 950 degrees centigrade. So it's the highest temperature on the system. It is a direct cycle gas turbine, and it's I don't think it's going anywhere, but it's interesting design. It's a direct compare. And what you can see is whereas PBMR ended up at 400 megawatts thermal, and that really was probably a bit much, the prismatic fuel gives us 600 megawatt thermal. So more power. But what you can also, I can take, given that the prismatic fuel handling is going to give them grief, they haven't built one yet. HTGR Poland, this is in Poland. NCBIR, I forget what it stands for now, but that's their version of CSIR in Poland. It's indirect for process heat applications, explicitly aiming at process heat applications. And what you can see, they've got siting sort of sorted out, they've got the engagement, they've got supply chain, but realistically, it's in early days yet. Kaleidos, it's radiant energies, I haven't heard of them before. It's 1.9 megawatts thermal, which is, it's got prismatic fuel, but I believe it is just simply you load the core with fuel, you put it out there, you run it for 10, 15 years, then you bring it back, and it's explicitly designed to be replacement for diesel generators. There's a microreactor for industrial and remote applications. Again, 700 degrees centigrade. HMR 100 is the South African with Stratec. It's coming from work done by, give me strength, the thorium team. It's got some engagement going on. But it doesn't appear, from the point of view, this is 2024, it's not being assessed by the NEA as being particularly far advanced. I know that Kelvin, which is on the list on the stream, but he'd have an argument about that. But again, 70 degrees centigrade, very classical. These 70 degrees centigrade is not really a challenging temperature for these things. Gives you steam conditions at about 555, 70 degrees centigrade with reasonable SGs, which is very much into the same league as current reactors. MMR, this is being a firm called USNC, which stands for Ultra Safe Nuclear Company. It's a prismatic fuel core. It is designed to have a single core built, installed, and you change the whole core out. It's an indirect cycle using molten salt. So that's what's interesting about it, is it doesn't have a steam generator. It uses an indirect cycle. So then you've got molten salt coming out, hot molten salt. So what you do with the heat is your problem outside the plant somewhere else. What's interesting is that it's nominally a US company being developed for application in Canada, and the entire engineering team sits in Pretoria and speaks Afrikaans, and ex-PBMR people. So what you can see is they're fully engaged. They've got fuel sorted out, licensing's hardly started, and so on. I believe that USNC is backing off on this project to move on to this project called the Pylon T1. This is being heavily supported by US military. It's got 1 megawatt thermal. It's again one of these things that's designed to be replacing a 500 kilowatt diesel generator, basically. And the fuel is well established because it's the same fuel as the previous design. They've built and tested the fuel, but it's not otherwise got far down the line. eVinci is a plant, and again, apparently it's designed by a South African who went to Westinghouse from what was IST Nuclear, which was a support company for PBMR, was then bought by Westinghouse, and he's now in the States. But it's a South African design. And again, it's the same sort of thing. It's 15 megawatt thermal using prismatic fuel because the fuel's not being changed. It's again transportable as a design. It's interesting because it formally declares it's using heat pipes as the heat transfer medium between the reactor and the outside world, which is interesting technology, which has great promise. And again, running at 750 degrees centigrade. So that's that. And you can see it's getting somewhere, but it's not moved much on licensing or fuel. XC Energy, 200 megawatt thermal. I apologize for my typo earlier. Full bed fuel, X Energy. So it literally is the carry on from the PBMR. It's done. They've got a contract. I don't know if it's a letter of intent or whether they're working with Dow Chemicals to make it will process heated to Dow Chemicals' plant in southern USA. And they're in early works with Dow Chemicals to actually install in their plants. Again, you have to go back to that concern I had earlier about those valleys of death. Getting someone to fund you to get over the next hump is a vital thing. Again, indirect cycle, again, 70 degrees centigrade. So that's basically it. I'm open to questions. I rushed through it quite quickly. It's half an hour. I apologize for my problems earlier, but I'm now passing back to Minx to handle the question side of things. I hope there are some questions. Minx?
Yes, thank you, David. Yes, can you hear me?
I can hear you.
David?
Yes, I can hear you.
Okay, great. Okay, excellent. Thank you. We don't have any questions as yet. I did ask the attendees if you have any questions, please type it in the questions panel, and we'll have David answering that. We'll give it a few seconds. While we wait for the questions, I just want to inform the attendees that there's a PDF versions of the latest issue of the What Now magazine, the April issue, in the handout section, which you can download, and the Training Academy brochure for CPD credits. So please check it out. We don't have any questions. I think our attendees knows everything about, or don't have any questions on Gas-Gooled Reactor.
And Minx, let me give a different discussion slightly. I think what was interesting to me, very much interesting to me, was when I took over as Chief Nuclear Officer in 2016 in ESCOM. I was asked by the then CEO and head of generation to restart the PBMR project, which is a question that often comes up as to why do we just build the PBMR? And my answer to that was very much like that diagram. I hadn't the diagram clearly way off at this point. I said, we've got the technology basis, we've got the designs, but we haven't got the supply chain anymore, because that was when we built up when we built the PBMR project. The supply chains are really important, because when you get to detailed design, you need the supplier of that component to be on board with you. Because this is like commercial. And we also got the whole infrastructure of the company. What I also said was that, in fact, we learned a lot from doing PBMR. And that's why it's interesting, and I didn't put it up here, and I could have done it, I think, could have done a bit more. We started working on what would we build as a high temperature reactor now, given what we learned with the PBMR. Because as you build the PBMR, you learn things as you go along, and then you say, wouldn't it be nice if we hadn't done this, we'd done something else? You know, minor changes, but you're just too late to change them. So then we came back, and what was interesting was we put together this concept of the advanced high temperature reactor. We first of all said we now understood how TRISO fuel works. It's quite an interesting concept. When TRISO fuel was first developed, it was developed in the 1960s in the UK. And for those who are interested, it was developed actually to be jet engine and rocket engine fuel. So days of nuclear rockets and nuclear airplanes. Never happened, but they were talking about it. And therefore, they wanted to have very high temperature, get gas turbines on with it. Now, it didn't work, but it was built. It was designed originally in Farnborough, an aircraft site in the UK. And then it was applied around the world, applied by different people around the world. And people found it wouldn't work and it would work. The Germans found it worked really well. The Americans found it worked really bad. And I explained that discussion if I agree with it. What was interesting about that was that they didn't know why it worked. They knew it worked, they didn't really know why it worked. I mean, you knew the barriers were there and everything else. We couldn't explain the phenomena we were seeing in the fuel at different temperatures. And what's really interesting is probably from about 2008 onwards, people started to understand what was actually happening with the fuel under severe conditions. And with that understanding, we now know how to make better fuel. So the current TRISO fuel, essentially your fuel temperature limit, realistically is at 1,300 degrees centigrade in operation and 1,006 in accident. TRISO fuel, you can do that with it, it's reliable and robust. The interesting point was that we'd done a lot of work at PMR on what advanced fuel could look like. There's a number of patents. And essentially what it meant was that we ended up with a situation where we're pretty sure we could build fuel that would go closer to the limits of silicon carbide and graphite. Just put in context, silicon carbide is good to about 2,300 degrees centigrade, and graphite doesn't melt, it sublimates at about 3,500 degrees centigrade. So we worked out that we actually could push the fuel temperature up to about operating temperature, about 1,006. And then accident temperature maybe 2,000. That was sort of very, very credible. So given that, we then said, okay, so we can push for higher temperature outlet. And that was the fuel guy said, yeah, we can do that. We don't want to work on the core design and how the core should be cylindrical or tapered, all kinds of clever things. But then we had another question of, okay, we've now got this gas coming at 1,200 degrees centigrade. What the hell do we do with it? Because you can't build a heat exchanger that will actually that temperature and meet nuclear safety standards. So we then we then put a high-speed gas turbine as the first thing the fuel saw on leaving the reactor, and that would be made by ceramics as well. We thought carbon composites or something else. Again, good to 2,000 plus degrees centigrade, and that would extract about a third or half the power out of the temperature and exhaust the gas now at about 670 degrees centigrade into a heat exchanger. So that was interesting. That was that little discussion. That got very interesting. Then we're going for molten salt heat exchangers, again compact, and no risk of steam coming into the gas circuit. And then we did the pressure vessel, and we said, why are we doing a steel pressure vessel? And we said, well, actually, we can do a concrete pressure vessel. We did the concrete pressure vessel, and that came out really, literally about 1/5 the price. So I'm not sure I believe the prices, but a lot cheaper than a steel pressure vessel. Clearly, you can't build those in the factory. You're going to build them on site. You can't pour concrete in the factory. So that's the. But also, we then said, okay, but how do we get the heat out of the reactor? You've now got the reactor running at full temperature. Everyone's very happy. When you trip the reactor and you lose all the power, how do you keep cooling it? So we then looked at the idea of putting heat pipes on the side of the core barrel. And these heat pipes would only start functioning. As heat pipes, they have a starting temperature, a stopping temperature. If you make the right material, and I think it was sodium, but I could be wrong. You end up with it not working below 200 degrees centigrade. It wouldn't have any heat transfer. And above that, heat transfer would be off. So the idea was then to put those around the core barrel. So what I'm trying to put on the table, and I'll just for information's sake, interest's sake, is that I believe at the moment the world is dominantly looking at building high-temperature gas-cooled reactors really are versions of the original concepts of the HDR module which is a German design from Interatom, part of Siemens, in about 1982. And they work. That's what the Chinese have built. And it works, it makes power, and it works reliably. I think that the big thing about HTRs is the potential going forward is enormous. And that's where for example, in terms of water-cooled reactors, we know enough about it to know where we've got to, and there's not much further to go. So as I thought, I still see no questions. Oh, sorry, do I see a question there?
Yes, David, thank you for that. We've got a question from Walter Mwelwa asking, when there's two countries involved in a project, who gets the responsibility of the licensing part of the project?
Ah, that is a fascinating question. Currently in the world standard is that the owner-operator of the plant is accountable for licensing. So at Coburg, for example, ESCOM is the licensee, nobody else. The French may have built the reactor, the Americans run it. So the question is, who's building the reactor? We're talking at Nexa, trying to go forward with the program of building an SMR on our site as the lead unit for the country. Almost certainly an external, vendor supporting us. And the vendor may bring the design, he may bring the money, he may bring everything, but ultimately the licensing will be a requirement of Nexa. The other answer to go with that is that approach is a real challenge to rolling out SMRs in general in Africa. Because the problem that we face is that if you go to some inventor country, Malawi, a small country, wants to build 100 megawatt, 250 megawatt SMRs, would make great sense for them. Their grid's very small, be very good for them. Low carbon, all the best stuff. The trouble is they then have to have their own licensing organization to license it. In other words, a national version of their version of the National Nuclear Regulator. And the vendor and the operator has to theoretically have an engineering team who's able to actually justify the design of the plant down to nuts and bolts. That means about 200 people in each organization. We can look at Coburg. Coburg has about that. Now, the problem with that is that you've now got your nuclear reactor with like 100 guys working on it, and you've now submitted 500 people who are supporting them. But the economics become unchanged. So one of the things is going to have to be the licensing of reactors in countries with no nuclear program and with a small SMR program is going to have to be worked on. And also, the SMRs are by definition standardized. As I mentioned earlier, they're very absolutely cookie cutter. The problem with then is that means that your licensing authority is being told you cannot change anything. So suddenly that is an interesting challenge. It's notable that Coburg has some minor differences from what the French have because of a different view held by the regulator in South Africa versus the regulator in France. Something the French have asked for, we've not done, and some things we've done, the French have said you don't need that. That works fine with 2,000 megawatts of power. It doesn't work fine with 200 megawatts of power. So that's my licensing discussion. Back to you, Minx.
Thank you, David. Another question from Nolufefe Ngalankulu, asking, seeing that there are still challenges with the supply chain, are there any countries that have taken up the SMRs and used for research purposes?
No one's doing it for research purposes because they're too big. I mean, Nexa's got two projects on the table now. One is to replace Safari, and one is to do an SMR. And then we've had discussions among ourselves of could we make the same thing? The answer is no, you can't. They're different objectives. So no one's done. The nearest you can say to that is that the Chinese, for example, on the high temperature reactors, built HTR-10, which is a 10 megawatt thermal plant at Tsinghua University. They built that in went started up in about 2000, 2001. They've used that as a vehicle to build their information base to help build their HTR-PM, which is 2 by 250 megawatts thermal. And that first twin unit, they're saying this is not a commercial machine. It's commercial linked to the grid. It's declared commercial, but it's seen as a demonstration plant, and they are using that as a vehicle to provide support to their later on HTR-PM 600, which is the 6 units linked to one turbine. I don't think it was doing it for research purposes, but a lot of people are saying the way to get to your final commercial machine is to build some lead machines getting there. And on some technologies, that's absolutely required. So, for example, in the States, not a gas, it's very interesting, it's not a Gascooled reactor, it's actually a pebble bed reactor using molten salt coolant. So if you can imagine this, you've got pebble bed, you've got pebbles, like Cuba, people had, and you don't cool it with helium, you cool it with a molten salt. So you have very interesting, and they're building very serious test rigs, including a 35 megawatt thermal reactor to prove this actually works. That's the nearest they're doing, but no one's saying I need a research reactor to build an SMR as my research reactor. We looked at it briefly. Well, we could always look at, could we buy an SMR to replace Safari? And the answer is not really. Not without affecting the SMR so much it wouldn't be an SMR anymore. In which case, why not build a cheaper thing, which is a simple research reactor? The German THTR, which was 750 megawatts thermal and 300 electrical, in Germany, started up in 82, I think, was shut down in 86, I think. Not for any technical reason, purely politics and money. Concrete pressure vessel. And in fact, as of today, all the gas-cooled reactors running in the world, with the exception of the Chinese HTRPM, actually have got concrete pressure vessels. So it's a very credible idea. We think it makes sense, but no one else is looking at it at the moment out there. It looks like it's just everyone's got more conservative after the PBMR was there. I can make that statement. Okay. I see no more questions. Am I right? Mix?
Yep, you're correct. I think that will also conclude the webinar for today. David, thank you very much for your time, and for the attendees. Thank you for your time and listening to this. Please be on the lookout for the advertising collateral for the next webinar on the 22nd of May, and we hope to see you there. Thank you all for attending today, and have a good one. Goodbye.
Cheers all.
Thank you, David.
Bye.
Bye.